naval warfare demands constant adaptation, pushing technological and design boundaries for strategic advantage. This relentless pursuit of innovation, however, incurs immense financial and operational risks, frequently leading to costly dead ends. The evolution of modern naval vessels reflects this tension, showcasing a spectrum from radical, high-stakes experiments to refined, battle-proven platforms. For decades, naval architects and strategists operated within established paradigms, incrementally improving existing hull forms and weapon systems. But geopolitical shifts, emerging threats like advanced anti-ship missiles, and the imperative for multi-domain dominance forced a re-evaluation. Traditional designs, while reliable, struggled to integrate cutting-edge stealth, power generation, or autonomous capabilities without fundamental redesigns. This created a turning point: either push radical and proven concepts or invest heavily in upgrading existing proven lineages. The choices made shaped not just individual ships, but entire fleet compositions and future operational doctrines. This script examines 8 pivotal vessels, each representing a distinct evolutionary path or a critical turning point in naval development. From ambitious, high-cost ventures that redefined what was possible yet proved unsustainable, to the steady, iterative refinement of successful platforms, and finally, to the specialized designs and autonomous future that challenge conventional thinking. We will dissect the mechanisms behind their design, their operational consequences, and the hard-nosed practical lessons learned from each. The Zumwalt-class destroyer, DDG-1000, represented a monumental, even radical, departure from conventional naval architecture. Envisioned as the future of surface combatants, its design prioritized stealth and advanced capabilities over traditional warship aesthetics and cost efficiency. This vessel was a direct challenge to established naval design principles, aiming to redefine littoral warfare and power projection. At its core was the futuristic tumble-home hull, an inverted bow design engineered to significantly reduce the ship's radar cross-section, making it appear as a small fishing vessel on enemy radar. This extreme stealth was complemented by an integrated power system, IPS, generating a formidable 78 megawatts. This immense electrical capacity was not just for propulsion. It was specifically designed to power future energy weapons, positioning Zumwalt at the forefront of naval technological advancement. The vessel also featured 2 advanced gun systems, 155mm cannons, intended for precision land attack support, further cementing its role as a multi-mission platform. However, Zumwalt's ambitious vision collided with stark economic realities. Each unit soared to over $4 billion, pushing the total program cost above $22 billion with research and development. This exorbitant price tag forced a drastic reduction from an initial 32 ships to just 3, fundamentally altering its intended fleet impact. Furthermore, the specialized ammunition for the advanced gun system proved prohibitively expensive, effectively rendering its primary land attack weapon impractical. Consequently, the Zumwalt-class now undergoes modernization, reconfigured to carry conventional prompt strike hypersonic missiles, a pivot aimed at restoring its strategic relevance. The Zumwalt stands as a testament to radical naval engineering, a vessel packed with groundbreaking technology. Yet, its story underscores the critical balance between technological ambition and practical affordability, demonstrating how even revolutionary designs can be curtailed by economic constraints and evolving strategic priorities. The USS Independence, lead ship of the second Littoral combat ship class, represents a different evolutionary path that prioritizes speed and modularity over traditional durability. Its most striking feature is the aluminum trimaran hull, a design measuring 127 meters with a 3,100-ton displacement. This configuration was engineered to provide a massive internal volume and a stable, wide flight deck while maintaining a shallow draft for coastal operations. The ship was built around a modular architecture, intended to allow rapid swaps between mine countermeasures, anti-submarine warfare, and surface combat packages. For organic defense, it carries a Bofors 57mm Mark 110 gun and a rolling airframe missile system. In terms of performance, the trimaran design achieved its goal of high-speed agility, capable of exceeding 40 knots. This speed was meant to enable sprint and drift tactics in littoral zones, where the ship could deploy unmanned systems and helicopters like the MH-60 Seahawk. However, the operational reality revealed deep flaws in the mechanism. The aluminum construction, while light, suffered from aggressive galvanic corrosion and structural cracking when pushed in heavy seas. Furthermore, the modular mission packages, the very heart of the Littoral combat ship concept, failed to materialize as promised. Instead of swapping capabilities in 24 hours, the process took weeks, and many modules never reached full operational capability. The practical value of the Independence was ultimately undermined by these technical and conceptual failures. It became a ship without a clear mission, lacking the armor for high-intensity conflict and the reliable modularity for specialized tasks. By 2021, the Navy determined that the cost of upgrading the early hulls to meet modern threats was prohibitive. As a result, the USS Independence was decommissioned in July of that year, after only 11 years of service. Its premature retirement highlights the danger of overcommitting to unproven modularity and lightweight materials, marking a pivot point where the Navy began moving back toward the proven reliability of steel-hulled destroyers. While the previous generation prioritized experimental modularity, the Arleigh Burke Flight Three, exemplified by the USS Jack H. Lucas, represents the calculated refinement of a proven platform. This vessel is not a radical departure but a systematic evolution of the Arleigh Burke lineage, designed to integrate massive sensor upgrades into a reliable, battle-tested hull. The centerpiece of this iteration is the N/Spy-6V-1 air and missile defense radar, which replaces the legacy Spy-1 system. This radar, combined with the Aegis Baseline 10 combat system, provides a quantum leap in sensitivity and processing power. The ship retains the familiar 96-cell Mark 41 vertical launch system, ensuring deep magazine compatibility with a wide array of SM-2, SM-6, and Tomahawk munitions, all while maintaining the structural integrity of a steel-hulled destroyer. The performance implications of this upgrade are profound. By shifting to the Spy-6 radar, the Flight 3 gains the ability to simultaneously track and engage multiple high-end threats, including advanced ballistic missiles and cruise missiles, at ranges and precision levels previously unavailable to surface combatants. This is not merely a sensor swap. It is a fundamental increase in the ship's defensive envelope. The added power demand of these advanced electronics required a significant upgrade to the ship's electrical generation and cooling systems, forcing a slight increase in displacement to approximately 9,800 tons. Despite this added weight, the platform maintains speeds exceeding 30 knots, ensuring it remains highly maneuverable within a carrier strike group. The practical value of this design choice lies in its operational predictability. Unlike experimental platforms that struggle with maintenance or mission package integration, the Flight 3 leverages a mature supply chain and a well-understood maintenance cycle. It serves as the backbone of the United States Navy, providing a reliable, high-density air defense asset that can be deployed globally without the risks associated with unproven technology. By focusing on iterative improvement rather than total reinvention, the Navy has secured a platform that balances cutting-edge capability with the ruggedness required for sustained, high-intensity naval operations. This destroyer proves that in the face of evolving global threats, the most effective path forward is often the mastery of existing, proven foundations. The Type 055 Ring-class destroyer represents a significant leap in Chinese naval modernization, emerging as a formidable platform that challenges established Western designs. Its sheer size, displacing 12,000 tons, and its impressive armament earn it the moniker Super Destroyer, with some analysts even classifying it as a cruiser. This massive hull accommodates 112 universal vertical launch system cells, a capacity exceeding that of many Western counterparts. These VLS cells are capable of firing a diverse range of missiles, including anti-air, anti-ship, and land attack cruise missiles like the CJ-10, providing substantial multi-mission capability. The combat system is anchored by the Type 346B active electronically scanned array radar, a powerful sensor suite comparable in function to the American Aegis system. This advanced radar provides robust situational awareness, enabling the detection and tracking of numerous threats simultaneously. Performance implications are clear. The Type 055 is designed for significant power projection, capable of engaging multiple targets at extended ranges. Its 30-knot speed, while not groundbreaking, is sufficient for operating within modern naval task forces. The integration of systems like the Type 1130 close-in weapon system and the HQ-10 missile system further bolsters its defensive capabilities against anti-ship missiles and aircraft. The practical value of the Type 055 lies in its potent combination of size, armament, and advanced radar technology, offered at a reported unit cost of approximately $920 million. This cost-effectiveness, relative to comparable Western vessels, allows for the rapid fielding of a large number of these capable warships. The Type 055 is a key component of Chinese strike groups, underscoring the nation's ambition to strengthen its power projection and maintain parity with global naval powers. It signifies a strategic shift towards building larger, more heavily armed surface combatants designed for sustained, high-intensity operations far from home waters. The Sejong, the Great-class destroyer, represents a significant leap in South Korean naval capability, built under the KDX-3 program. These vessels are the most powerful warships in the Republic of Korea Navy, directly integrating the American Aegis combat system, a testament to robust international defense partnerships. Their design philosophy emphasizes overwhelming firepower, achieved through an immense battery of 128 vertical launch system cells. This VLS capacity notably exceeds that of American Arleigh Burke-class destroyers, positioning the KDX-3 as a formidable regional asset. The Aegis combat system, coupled with the Spy-1D-V radar, provides sophisticated multi-target engagement capabilities. This allows the Sejong, the Great-class to simultaneously track and engage numerous threats, including aircraft, anti-ship missiles, and ballistic missiles, especially with Batch 2 upgrades. Its armament includes SM-2 anti-air missiles, Hyunmoo-3 cruise missiles for land attack, and SSM-700K Haesong anti-ship missiles, alongside torpedoes. This diverse missile loadout ensures mission flexibility across various operational scenarios. Performance implications are clear. The KDX-3 is engineered for sustained power projection and area defense, capable of dominating its operational environment. Its 30-knot speed is adequate for operating within modern naval formations, ensuring it can keep pace with carrier strike groups or conduct independent patrols. The practical value of the Sejong, the Great-class is immense, forming the backbone of South Korea's surface fleet and serving as a critical component of regional security. With a unit cost estimated at $1 billion, these destroyers offer substantial firepower and advanced combat systems that rival or surpass many Western counterparts. Their high VLS cell count and Aegis integration make them potent deterrence and power projection platforms, capable of projecting influence across East Asia. The complexity and cost of maintaining U.S. origin systems present a known challenge, but the strategic advantage gained by these highly capable vessels underscores their importance in maintaining regional stability and national defense. The Visby-class corvette represents a distinct evolutionary path in naval design, prioritizing extreme stealth and multi-role capability within a smaller platform. Unlike larger, more conventional destroyers, the Visby was conceived as a pioneering stealth warship, optimized for challenging littoral environments. Its most striking feature is the hull, constructed from carbon fiber composites, which drastically reduces both its weight and radar signature. This advanced stealth technology extends to its design, minimizing thermal, acoustic, and radar profiles, making it exceptionally difficult to detect by adversaries. Measuring 72 meters with a displacement of 640 tons, the Visby-class achieves speeds exceeding 35 knots. Its armament includes RBS-15 anti-ship missiles, 400mm TP-45 torpedoes, and a Bofors 57mm artillery gun, providing a potent offensive and defensive capability. The design integrates these weapons and sensors to maintain its low observability, ensuring systems like the exhaust are hidden to reduce thermal signatures. This combination of speed, stealth, and integrated weaponry allows the Visby to perform diverse roles, including anti-ship, anti-submarine, mining, and patrol operations, making it a versatile asset for coastal defense. The practical value of the Visby-class lies in its ability to operate effectively and survivably in complex, congested littoral zones, such as the Baltic Sea. Its extreme stealth provides a significant tactical advantage, enabling surprise attacks or covert surveillance missions. While its limited range endurance, and smaller payload capacity are known trade-offs for its specialized design. These corvettes are crucial for nations requiring potent, yet discreet, naval presence in specific operational theaters. The Visby's innovative approach to stealth and multi-role functionality demonstrates a successful adaptation to the demands of modern coastal warfare. The Skjold-class corvette represents an extreme evolutionary niche, prioritizing raw velocity and low observability to dominate littoral environments. Unlike conventional displacement hulls, the Skjold utilizes a surface effect ship design, functioning as a hovercraft catamaran hybrid. This mechanism traps a cushion of air beneath the hull, drastically reducing hydrodynamic drag and allowing the vessel to achieve speeds exceeding 60 knots. The structure relies on a sophisticated blend of composite materials and aluminum to maintain high structural integrity while keeping weight minimal, which is essential for sustaining such high-speed performance in choppy coastal waters. The performance implications of this design are profound. At 60 knots, the Skjold can transit vast stretches of coastline or navigate complex fjord systems with a speed advantage that few adversaries can counter. Its low detectability is not merely a product of its sleek, radar-absorbent geometry, but is further enhanced by its ability to operate at high speeds, which complicates tracking and targeting for enemy sensors. Armed with 8 naval strike missiles and an Odo Melara 76mm super rapid gun, the vessel packs a punch disproportionate to its 274-ton displacement. However, this extreme specialization comes with operational trade-offs, specifically regarding the high maintenance requirements of the air cushion system and limited endurance in heavy sea states. In practice, the Skjold-class serves as a highly effective rapid response asset for the Norwegian Navy. Its primary value lies in its ability to strike and vanish within the intricate geography of the Norwegian coastline. By leveraging its speed to exploit the hide-and-seek nature of the fjords, the Skjold can execute hit-and-run tactics that force an opponent to expend significant resources just to locate and track it. While it lacks the blue water endurance of larger destroyers, its role is not global power projection. It is the absolute denial of coastal access to any adversary. The Skjold proves that when a naval force defines its operational theater with precision, it can trade general-purpose versatility for a specialized, high-speed capability that fundamentally shifts the local balance of power. This platform remains a benchmark for littoral agility. Sea Hunter represents a stark departure from traditional naval platforms, embodying a future where autonomy dictates operational capability. This unmanned surface vessel, or USV, is not merely a remote-controlled boat. It is a sophisticated AI-driven platform designed for extended, crewless missions. Its primary directive is the persistent tracking and detection of submarines, a critical intelligence-gathering role that can now be performed for months at a time without human intervention. This capability dramatically reduces the logistical burden and risk associated with manned patrols in potentially hostile waters. The technical specifications underpinning Sea Hunter's autonomy are crucial to its operational viability. Its trimaran hull provides exceptional stability, essential for maintaining sensor accuracy and operational readiness during long deployments. While its speed, estimated between 20 and 30 knots, is not groundbreaking, it is sufficient for its intended role of shadowing submarines. The true innovation lies in its advanced artificial intelligence and sensor suite, which allow it to navigate complex maritime environments, avoid obstacles, and analyze situations independently. Developed as a prototype by DARPA and the U.S. Navy, Sea Hunter's unarmed nature emphasizes its focus on reconnaissance and intelligence, positioning it as a leader in the emerging market for autonomous naval systems. Its recent transition to U.S. Navy testing for long-range tracking underscores its potential to redefine maritime surveillance. In practical terms, Sea Hunter offers a glimpse into the future of naval warfare and maritime security. Its ability to operate continuously for extended periods, coupled with its autonomous decision-making, allows for persistent surveillance that was previously unachievable or prohibitively expensive. This opens up new strategic possibilities, such as establishing a constant, low-risk monitoring presence in critical sea lanes or contested areas. While regulatory hurdles and cybersecurity remain challenges for all autonomous systems, Sea Hunter's development signifies a significant evolutionary step, demonstrating that the future fleet may well consist of highly capable, crewless vessels working in concert with traditional manned platforms. It's a hard-nosed, practical application of AI to a persistent naval problem. Naval evolution remains a brutal, high-stakes interplay between technological ambition, economic reality, and shifting strategic necessity. We have seen that radical departures like the Zumwalt often collapse under their own complexity, while the iterative refinement of established platforms like the Arleigh Burke ensures long-term operational relevance. Simultaneously, specialized designs and the rise of autonomous systems like Sea Hunter signal a fundamental transition in how we project power at sea. The verdict is clear. Sustainable naval superiority requires balancing disruptive innovation with proven, scalable platforms. Future dominance belongs to those who successfully integrate these hyper-advanced manned vessels with the emerging autonomous